In this video, I'm going to go over briefly what a coroutine is, how it works under the hood, and why we use it in Unity. So I'm going to start with the process pump, and all coroutines are process pumps. So this is the simplest process pump you can get. It has an array of actions, and this array is called onStart, and it goes through those actions and executes every one of the actions in the list. Now this particular code will lock up the application right now because this process pump is very simple, and there are ways to upgrade it so that it doesn't lock up the application. But the reason why it would lock up the application is because it has no concept of a wait. And if we were running in a multi-threaded context and we ran this process pump on its own thread, then completely occupying the thread might not be such a problem. It might be an acceptable thing. And so we could run this sort of process pump. Back in, well, let's just say 10 years ago or so, when working in Windows, one of the core features of Windows that you had to get used to in order to develop for that platform was dealing with the message pump that it was using. And it would take this concept of a process pump that is shown here and change it just a little bit. They, instead of running a delegate to a process, it would pass in events that had happened in your process, and your process would execute those events. So whether the screen needed to draw or the mouse was clicked, each one would create an event, and each event would execute a particular line of code. Nowadays things are a little more complicated. There are layers, and we won't get into that. But process pumps have been used all over the place, and Unity has made the decision to put all of the scripting logic on a single thread. And some people have assumed that that makes it more primitive, but it actually works very well. Most of the rendering goes on in other threads. It is just the scripts that you work with on a daily basis that all operate on a single thread. And there are a whole class of bugs in .NET that plague most platforms, which are thread safety issues. These are pretty much the nastiest bugs you can ever encounter. These are the type of bugs which make you lose your hair. These are the type of bugs which make you yell at your spouse. These are, for instance, when your application quits for no reason and gives you no indication of what the cause might be. These are when you set a variable to one thing, but 1 out of 1,000 times it changes at some random point in the application. These are when an exception is thrown, but it's not thrown every time. It's thrown maybe 0.01% of the time that a particular code block is executed. These are really, really nasty bugs. That kind of stuff never happens in Unity in your scripting because you're not using multiple threads. Everything's running in the same thread. And let me go over what an Ienumerator function is and a yield return structure. So this here is how an Ienumerator was originally meant to be used. The .NET Foundation came up with Ienumerator as a way to return values one at a time from a list. So down here, I have this Ienumerator function. Now this Ienumerator function, even though it looks like a coroutine, is not a coroutine. It is not a coroutine because it is not designed to execute over a long period of time. That's what a coroutine does. It is designed instead to return values one at a time from this function. So how this function works is this while loop executes this move next, and every time it goes move next, the first time it runs into the program and starts from the beginning of this function here and returns 72. The next time it returns 74, and each time it executes move next, this current value, which is an int, gets set to whatever was returned by the yield return. So current gets set to something, it gets set to something else, it gets set to something else. Each time it gets set to something else, we will output that to the console in this case. And this is how Ienumerator functions were designed to be used, to return a list of values one at a time. And this whole structure was created in order to make that happen. There are other aspects of Ienumerator functions which make them more efficient than just iterating through an array like we are doing here. Really, the things that make it more efficient is that they can be wrapped. this yield return can be returning to another Ienumerator, which only takes every other element, for instance, and returns that. And so without changing the original function or the list itself, you can return objects that pretend to change the list, but don't actually make any changes. So for that sort of a problem, Ienumerator was considered to be an excellent solution and worth creating this really odd structure. They had to create this yield return statement, which is not used anywhere else in C#, and they created a yield break statement because they found that they needed a way to end the function prematurely. And in any other function, you would just use the word return, but they'd already made a statement called yield return, and the word return and the statement yield return are just too similar. So they changed it to yield break. But if you look at this Ienumerator function as what it's designed to do, right now it is returning a value. It is yielding the function and then returning a value to whoever's calling the function. And when you finish doing whatever you're going to do with that value that was returned, it comes back to that point in the code. And that is the key here. That is why coroutines work so well. When you make a return command in a normal function, that function doesn't resume where you left off. When you make a yield return command, it does. And this is why we use the Ienumerator structure for coroutines, even though that isn't really what they were made for. It is the only place in .NET where that sort of functionality is built into the compiler. And you might be able to make it yourself using some complicated system of delegates or callbacks, but this way is clean and fast, and it doesn't break when you recompile. That allows you to go here and say yield return 0. But of course, this is not an Ienumerator function, so it has to be an Ienumerator. Now this function has the capacity to not take up all the processing. It will yield itself and return a value, which is 0, and whoever called the function has the ability to do something about it. Now in this case, we called the function directly, which is a bit of a problem because we're not actually looking at the current value of this function, and we're not actually planning on calling move next ever again. So what we need in order to make this a proper coroutine is to hook this into something that does this part here. And maybe it does a little more. Maybe it's quite a bit more complicated, but essentially hook it into a function that will call it over and over again every frame, look at the value that it's returning, do intelligent things with that value. And in this case, we can either use Unity's version of it, or we can use the mech version of it. So if we wanted to use the mech version of it, we would include movement effects, and then we would go here and we would say timing dot run coroutine. And we're running the process pump. So what .NET does in this case is the moment you use a yield return in a function that returns Ienumerator, it wraps it in a very special type of function pointer, one that has the move next functionality and has the current functionality. The run coroutine function will run a loop which will execute until a yield return happens, and then go do other things and eventually return the next frame and continue where it left off. So let's see that in action. One thing that I haven't done here yet is actually initialize this array. So I'm going to have to do that real quick. I'm going to have to say processes equals new array. And I'm just going to use a lambda here because lambdas are so easy. The new array is going to take transform, and it is going to set it equal to, let's set it to up. And put a semicolon after it. Now this should run every frame, set the position to up. Let's see if it compiles. Let's put some action there and fix our little spelling error. Now it should compile. And we'll see that the position will be set every frame to y equals 1. And also this other thing is being run, which of course, as you can see, does every other number. So that is this being run here. Of course, yield break doesn't matter. So that is how a coroutine runs. If this was set to something else, it could be anything else. It would run any list of actions. And of course, Unity's coroutines are basically the same animal as Mech coroutines. Mech coroutines are just a little bit more efficient because of the way that they're implemented and allocate less memory, and I've added more features to them that the Unity coroutines don't have.